All right, good evening, everyone. I thought since Wednesday we're going to do review, I thought you'd rather have that review session earlier than Wednesday. So I will record that now and get it uploaded. So when we ended this morning's lecture, we were talking about SN2 and E2, and we left off with the stereochemical outcome for each reaction. And so we said that SN2 always goes with physical inversion of stereochemistry at carbon. And the E2 has a sort of the stereochemistry of the substrate is reliably translated to that in the alkene product. And the way to figure that out is to arrange the proton to be eliminated and the leaving group bonds in an anti-periplanar orientation, and then look at which substituents are on the same side in the line wedge diagram or in a Newman projection, and those will end up on the same side of the alkene. So we'll spend essentially the rest of our time here just reviewing all of the different parameters for these two reactions, and now we'll move on to substrate. So okay, and so for an SN2 reaction, most often the substrates are going to be methyl and primary, and sometimes secondary. So methyl is always the best, and when I say the best, I mean the fastest, and then tertiary will be the slowest. Or sorry, secondary will be the slowest. Okay. And the SN2 displacement is going to be favored when our substrate is not branched. Okay. Let me say one other thing too: is never tertiary substrate, never tertiary or neopentyl. And you'll recall that neopentyl is this type of structure where you've got a tert-butyl group at the beta position. So even though that is nominally a primary substrate, because of that substitution at the beta position, you never do an SN2 at that center. Okay. E2 is also favored for primary and secondary substrates. And obviously you can't eliminate from a methyl. And as we discussed in the book or in the other lectures, these two reactions are competitive with one another. And so one of the parameters that you need to consider is the degree of beta branching on the substrate. Okay. And so what we say is that the SN2 is favored for unbranched substrates, and the E2 is favored when you start to have more branching. So okay. And so, for example, if we just considered a secondary substrate like 2-bromopropane, okay. Oops, sorry about that. Okay. Of course, the carbon bearing the leaving group is the alpha position. The next ones out are beta. And as I start to increase the substitution at the beta position, the E2 elimination becomes more favorable. And so, for example, so here I'm only modifying one of the beta positions, but we're iteratively introducing another methyl group in place of each beta hydrogen. And so as we move from left to right, we get increasing E2 at the expense of SN2. Okay. And we went through this in the lecture, so I won't redo it here, but you can go back to those notes. There's a conformational effect that explains this. And so you can orient the substrate in such a way that hydrogen is syn to the leaving group, as long as you have one beta hydrogen. As you start to substitute those beta hydrogens for methyl, you start to have to access higher energy conformers to have that presentation of the beta hydrogen. And then finally, when you get to the T-butyl, and it's now neopentyl, you can't present a beta hydrogen, and so the reactions just become virtually impossible. Okay. And so, okay, so that's what I wanted to say about the substrate. So basically, at the top, these are the possible substrates for an SN2 or an E2, and these are the effects of these are the characteristics of the substrate that will favor one over the other. Okay. All right, I'll just say a couple things about the leaving group because that's arguably the most straightforward. And the effects here, sort of the characteristics of the leaving group sort of equally affect both the SN2 and the E2 pathways. So we don't see any differentiation of those pathways depending upon our leaving group. And so really we just want to know, what are good leaving groups and what are bad leaving groups, okay? And a general rule of thumb is that good leaving groups are those where the conjugate acid of the leaving group has a pKa less than 0. So okay, and bad leaving groups are those where pKa is greater than 0. Okay, and so bad leaving groups will not participate in an SN2 or an E2. Okay, and so for example, if I have some sort of 2 substituted propane, and we can list we'll list the X groups here. So we'll say, for example, X equals OH, X equals NH2, X equals F, X equals I and BR, let's say. I'm not going to list all the possibilities. But the pKa then of HX, okay, is going to be about 15, 36, 3.2, minus 10, and I think about minus 7, okay? And so the HX, just to be super clear, HX is H2O here, is ammonia, H3N is HF, is HI, is HBr, okay? And so we would say that these are OH and NH2 are bad leaving groups. Ditto for fluoride. I should continue that out. Okay. And then the I and Br are going to be good leaving groups. Okay. And we haven't talked, there are many different types of leaving groups. We haven't talked about anything but halogens yet. So really, this is one instance where it might be just easier to memorize and know that for us, the leaving groups that we know about and that we consider are Cl minus, Br minus, and I minus, okay? We haven't actually talked about others. There are others. But these are the ones that you're going to see most frequently. They're also the ones that are used most frequently in practice, okay? And then the final bit is the relative ability of the leaving group. So how, if it is a viable leaving group, how easy is it to displace or eliminate it? And the answer is, again, follow the pKa's of the conjugate acid. The most acidic, the leaving group with the most acidic conjugate acid will be the best one. So okay, so iodide is greater than bromide, which is a better leaving group than chloride, okay? All right, so on the next slide, I want to talk about what I'm going to carefully call the reagent here. And the reason I'm calling it the reagent is because we're going to try and outline the factors that lead that reagent to behave as a base or a nucleophile. Okay, so if it's a base, it's pulling off a proton, it's doing the E2. If it's a nucleophile, it's attacking carbon, it's doing an SN2. Okay, so the question is, when does a reagent behave a base, which is E2, when does a reagent behave as a nucleophile? I think Larry's going to jump up here in a second. Let's see. Yeah, he's getting ready. Here he comes. All right. So when does our reagent behave as a base? When does it behave as a nucleophile? And the most important thing, here he is. Say hi, bud. What's up, buddy? Oh, he's a good boy. He's a good boy. Yeah, you're a good boy. He's a very nice guy. He's very good with Alice. He puts up with a lot of grabbing and hair pulling and fingers in ears and doesn't seem to get too perturbed. All right. So the most important thing is the sterics of your reagent, okay? Okay, so is your reagent bulky? Okay, and so, for example, terbutoxide. Okay, this is very bulky, and because the reagent is very bulky, it has a hard time getting into carbon. Remember, the way to conceptualize it is, the carbon atoms to do the SN2 displacement are at the core of the molecule. The hydrogens are on the periphery. So the hydrogens we need to access for an E2. So they're much more accessible. And so if I'm big and bulky and take up a lot of room, it's going to be harder for me to get to a carbon than it is to a proton. And so terbutoxide is very bulky, and so generally favors E2, okay? If the answer to that question is no, so if reagent is not bulky, SN2 predominates. And again, what do we mean by not bulky? We mean, for example, ethoxide or methoxide, if we're just talking about oxygen-based nucleophiles. Okay, so so that is. Let me just check real quick here. So that is really as deep as you need to go when you're thinking about the contributions of the reagent. Okay, is it bulky or not? And if it is, it's going to favor an elimination. If it's not, it's going to favor a displacement. And I wanted to say this morning, displacement is always favored inherently. So like, we sort of start with the idea that we're going to do a displacement, and then there are factors that mitigate that and push it towards an E2. And the reason it's favored is that it's favored on thermodynamic grounds. So you're converting sigma bond to another sigma bond, whereas in an elimination, you make a weaker pi bond. And then you're also almost always going to be making a stronger bond to the nucleophile than to the leaving group. That's not always the case, but there's a strong thermodynamic driving force, thermodynamic preference for displacement. And then there's also the kinetic effect that we talked about when we were discussing the orbitals this morning. So we said that the CX, this carbon leaving group bond, is polarized behind carbon. You have a big lobe there, okay? And so you can get really good overlap with the nucleophile. But when you're doing an elimination, you're pulling off a proton, and proton and carbon have almost the same electronegativity. So you don't get any polarization of the bonding or anti-bonding orbital. And what that translates to is that the degree of orbital overlap is not as good. And so transition state is going to be a little bit higher in energy. So yeah, so it may be helpful to think about it from that perspective. Like you're sort of starting from a position of displacement, but then there are factors that drive it towards elimination, okay? All right, so so what are the types of questions that you should be able to answer in terms of, am I going to get an SN2 or an E2, okay? And again, we're not going to ask you to split hairs or split atoms, on this one. But you should be able to make some types of judgment calls. So so for example, if I have 2-bromobutane which reagent, T-butoxide or methoxide, gives more E2. Okay, so that's a question that refers to the structure of the reagent. But then certainly questions that refer to the structure of the substrate. So for example, if you were considering these two substrates, so 3-bromopentane and 2-bromobutane, which one would you expect to give higher percentage of elimination product when you treat with, for example, methoxide? So okay. All right. So again, those are the types of questions, things that we want you to be able to answer. We're not going to ask you, to compare 2 or 3 different variables in the same question. I think that, that just becomes debatable very quickly, So it'll be sort of single variable, which way, when I change that variable, is the system going to be steered? Okay. All right. Let me go on then to nucleophiles or nucleophilicity. So all right. And so remember that we're able to draw a few different trends to anticipate the relative nucleophilicity of pairs or sets of reagents. And so when you have the same atoms, nucleophiles, or let me just, reagents with conjugate acid with higher pKa are better nucleophiles. Okay, and so, for example, if I have hydroxide and I have acetate, the question is, which one of these is a better nucleophile, right? And you would look to the acid. So the conjugate acid of these is water and acetic acid. And the pKa of the conjugate acid is about 15 and 4.72. Okay, and so water is less acidic than acetic acid, and so hydroxide is a better nucleophile, all else equal. Again, we're not gonna confront you with 2 variables at once. All else equal, hydroxide is a better nucleophile. Okay, and the explanation for that is simply that because water is less acidic, hydroxide is less stable, it's higher in energy, and so the system as a whole is closer in energy to that transition state required for nucleophilic displacement. Okay. The other generalization we can make is that when you have atoms in the same row, it's very easy. It also follows pKa. So okay, and so if I have our second row elements, so we would have carbon, nitrogen, and then oxygen, okay? We can go and look to its conjugate acid. So the conjugate acid of the methyl anion is just methane. Ammonia, or amide is NH3, ammonia. Hydroxide is water. And the pKa of the conjugate acid is about, this is on the order of 50. That's a rough estimate. This is about 36, and this is about 15, okay? So the methyl anion has the least acidic conjugate acid. It is the best nucleophile. And so the rank order would be like that, with water being the weakest, okay? And that's what plays out in practice. You know, we don't, the hydroxide in sort of the pantheon of nucleophiles is actually not a great one, but carbanions in fact are, and amidions in fact are, okay? So those are the easy trends. Where it gets tricky is when we go to looking at atoms in a column. And this is where we need to bring in solvent effects, okay? So okay, so the atoms are in the same column. The question is, what's the better nucleophile? And the answer is, it depends on the solvent, okay? So okay, and so if we're considering the halides, for example, fluoride, F minus, chloride, bromide, and iodide, we can then say, okay, what are the pKa's of the conjugate acids? And so we've got 3.2, minus 6, minus 8, minus 10, okay? And again, all else equal, so we're going to assume that we're doing a nucleophilic displacement. What's going to be the best nucleophile? And it will depend on the solvent. So if we do, for example, DMF, which I'll just remind you, we've already seen this, but DMF equals N and dimethyl formamide, which is this structure. Okay. If we're in DMF, the relative rates are about greater than 3, 2.5, 1.3, 0.4. And so fluoride is the fastest. And iodide is the slowest. okay? Or fluoride is the best nucleophile, iodide is the worst nucleophile in DMF, okay? And so the key is that DMF is a polar aprotic solvent. If we change the solvent and we say, okay, let's go to methanol. And so this is a polar protic solvent. Okay. Then the relative rates change. So we're at about 5 by 10 to the minus 8. For fluoride, 3 by 10 to the minus 6. For chloride, 3 by 10 to the minus 5. For bromide, 0.3 for iodide. And so fluoride is the worst, it's the slowest, and iodide is now the fastest. Okay, and so I'll give you the explanation for that in 1 second, but all of these rates for both solvents were pulled from the same displacement. And you'll notice that the reaction rates are much greater in DMF than methanol, and that is generally true. Nucleophilic displacement reactions are most efficient in polar aprotic solvents, and this will be clear why in a second. So let me just say SN2. Okay. And so what is the rationale for these, for both the orders in the different solvents and then the change in order going between the two solvents? It has to do with the way that the solvent interacts with the nucleophile, okay? And so okay, and so we need to understand what those interactions are between the substrate and the nucleophile. And so it's important, or substrate, the nucleophile and the solvent. It's important to remember that when we have a nucleophile, like a halide, it's X minus, it always comes with Y plus, right? It always, sodium fluoride, lithium chloride, whatever. So okay, and so if we hold the counter ion Y plus, okay, we can ask the question, what is the effect, because we only want to change one variable at a time, what is the effect of the solvent on the X minus? So okay, and so if we start with DMF, so that's a polar aprotic. Okay. graphically, and let's say just for sake of discussion, we're going to use Y plus equals sodium. Okay, just so we have a real atom in there. When you put a sodium halide, sodium fluoride into DMF, okay, there's going to be solvation. What does the solvation mean? What does it even mean, right? It means solvation is the interaction of the solvent with the reagent, okay? And so we say it gets solvated. What specifically does the solvation look like? You get coordination of the solvent, in this case for DMF, the carbonyl oxygen to the cation. Okay, in that manner there. And what we say is that this solvent coordination, the solvent are like, people surrounding one person. Suppose two people go into a room and then one person gets surrounded by a bunch of other people, okay? That's like the solvent surrounding the cation. The other person that came in the room is kind of left alone, right? Is standing alone. And that is your X minus. So solvent, when it's polar aprotic, such as DMF, surrounds Y plus, Na plus in this example, okay? When it surrounds Y plus, what does that do? That leaves X minus alone, or what we call naked, okay? Okay. You can't draw a similar type of interaction between DMF and any of the X minus atoms. It just there's no way to do it. Okay, and so the cation gets strongly solvated. The anion is left alone, sort of hanging out there in solvent without a whole lot of stabilizing interactions. And so then we ask the question, what's the relative reactivity of like an isolated X minus, of these isolated X minus anions? And that tracks with pKa, right? Because pKa measures directly the stability of the species on either side of the equation. So in this case, then the energy of fluoride in DMF is going to be highest, and that is because HA has the lowest, has the highest pKa. Let me clean this up here real quick. Okay, so HF has pK of 3. That's higher than any of the halogen acids. And we know that the higher the pKa, the less stable the conjugate base. So fluoride is going to be less stable than iodide unless there's any other factors that influence that stability. And when you're in a polar aprotic solvent, you essentially don't get any sort of really strong interactions between the solvent and X minus. And so it's not exactly the same, but it's sort of like if you were in the gas phase and you just had an isolated ion, where you're really just looking at the stability of that species. And so so fluoride, most reactive, least stable, going to be the best nucleophile. Iodide, most stable, least reactive, poorest nucleophile in a polar aprotic solid. Okay. And so the next thing then is, what about polar protic solvents? Okay. And the key difference here is that whereas in DMF, we had a very strong interaction between the solvent and the cation, but not really between the anion and the solvent. In a polar protic solvent, both species will interact very strongly with the solvent. So okay, and so consider methanol with sodium fluoride in there. Okay, or let's just say, let me just make it NaX. Okay, so the interaction of the sodium with the solvent is similar to what we saw with DMF. You have sodium cation, you have lots of methanol with lone pairs around it. And that will coordinate to the sodium, okay? The difference here, though, is that the X minus is going to be able to interact with the solvent in a way that it couldn't when the solvent was polar aprotic, and that specifically is going to be a hydrogen bonding interaction. So X minus is going to also see these protons in methanol and want to form a network of hydrogen bonds with them, okay? And so to get to the sort of the answer, we have to ask the question, how does this hydrogen bonding affect the energies of the different X minus species, okay? And because fluoride has the least acidic conjugate acid, it's going to hydrogen bond most strongly. So the interaction of F minus with methanol is stronger than Cl minus with methanol, which is stronger than Br minus and I minus, okay? And so if you were to put these onto an energy diagram, we would have F minus, Cl minus, Br minus, and then I minus. And this is the ranking in the polar aprotic solvent. And then when you switch to a polar protic solvent, the relative order changes. So now F minus is at the bottom. That's followed by Cl minus, Br minus, and I minus. And so, you know, we can connect these lines if we want. Okay. So the relative energies of these species all change when you go from a polar aprotic to a polar protic. And the reason is that the basis for the change is the difference in the hydrogen bond strengths. And so F minus forms strongest H bonds to solvent. I minus forms the weakest. Okay, and so if you just consider sort of the distance that F is traveling in that chart on the right here, the delta E between the two solvents is greatest for F minus and lowest for I minus. And so it's almost as if you're taking, if you consider the system, the substrate and the nucleophile, when you put that in a polar protic solvent, you're dragging the entire energy of that system for fluoride down very far because the fluoride is much more stable. And so the fluoride is going to be surrounded by all of these hydrogen bonds. In order to go in and attack the substrate, I need to break up that hydrogen bonding. And so you have this large enthalpic penalty that's associated with it. So okay, and so it costs the most in terms of bond enthalpy to have fluoride react with a substrate. Costs more than chloride, more than bromide, more than iodide. Okay, so those are the factors. And again, to give you an example of the type of question that we would ask, you saw these in the practice exams. What's the relative nucleophilicity in solvent A or solvent B? Or you've got two solvents, which one is iodide a better nucleophile in? That type of thing, changing one variable at a time, okay? All right, so that concludes the review that I wanted to do. I'm going to ask the TAs to cover SN1 and E1 in the review session. It's a lot less material. It really pertains to the substrate and the base and the solvent, but in ways that we've already seen here. So there's not a lot of new material there. So hopefully they can cover that very quickly. And that's all I want to say. So good night and good luck.